Actually, I'm not sure that I really want to give this presentation anymore after having given the symposium yesterday, and Dave's doing a great job. And this is stuff that I've been doing for 5, 6, 7, 10 years. And I'm still figuring out how the stuff that I will be presenting in a minute fits with the stuff that we've been presenting yesterday. And now the Days is kind of moving to an affordance-based control model for getting fly balls. Really trying to prove that people use the Chapman strategy seems a little bit out of date. But still I'm going to do that, and I think actually that it's still worth the effort. It's not that far away from the stuff that we've been doing. So let's go and let's see where I'm going. So running to intercept fly balls, how does a fielder get at the right place in the right time? And most of you know the Chapman strategy, optical acceleration, cancellation. So cancelling optical acceleration will get him or her at the place where he or she needs to intercept the ball. And I've used this graph, and they've used this graph, so you may be familiar with this. The idea is that there is this ball flying a parabolic trajectory. That was the analysis that Chapman did, and Claire did at some point. And ball follows a parabolic trajectory, and if you're standing right at the spot where this ball will be arriving, then if you look at the optics, then the projection of that ball on an image plane will rise at a constant speed. And the same is true if you're running to the interception location at a constant speed. So the idea is that from getting in a situation in which the image of this ball rises at a constant speed, you know that you will arrive at the interception location at the time that the ball will arrive there as well. Without knowing, and that's the thing that Dave pointed out, and that's why it's kind of tricky to figure out the affordance of catchability from this acceleration, without knowing where and when that time and that position will be. So, but the idea is that this would help you kind of run to this interception location. So optical acceleration would help you, would tell you that you're on the right track to arrive at that position. I think there's a few things that we should realize at this point, I would like to point out, is we always talk about optical acceleration, but really what we need to know, or what this story is about, is a constant optical velocity. So if we're talking about acceleration, what we really mean is not the second derivative, so order 2 in the new lingo, but we really need to know that it's not 1. It's something that's other than 1. So we need to know that, or this fielder needs to know that optical speed is not constant. And you can do that in different ways. So optical acceleration is one way of doing that, but I think we've realized for some time that our official system is not very well, not doing very well in picking up acceleration per se. So people have come up with other ideas. So there's this thing called the velocity ratio, which is defined as an increase in speed defined by the average speed. Doesn't seem to work very well either. But the things look a lot like each other. So I think that's important to realize. Okay, so if fielders would use an optical acceleration strategy to regulate their movement to get at that interception location, then this should show up in where they start running. Because at some point they are standing there and optical speed is not constant anymore, and that's the point that they know I should start doing something, right? So what we thought of doing, what the experiment was about, is look at these running initiation times, a little bit alike what Dave was presenting, and looking at the times that people say, no, I can't catch that ball anymore. So optical acceleration at least informs you that you need to start running back or running forward. And we've known that the patterns of judging passing sight are consistent with the use of optical acceleration. So that's stuff that, and when I'm talking about doing this for a long time, this is a paper in 2003 in a cave in Amsterdam. Both Claire and I were still in Amsterdam. This is the cave, and we had people kind of judge and catch fly balls in this cave. So people like this, they had this kind of thing in their hands, and in some of the one of the experiments, we asked them in the same way that they asked people just a second ago, with this kind of virtual fly balls, is this going to go over your head, or will it be landing in front of you? And we were looking at the time that they pressed their buttons. And these were the results, part of the results. When you had these different balls flying different distances from where they were standing, so these balls could fly 5 meters in front of them, or pass 5 meters in front of them. They would fly from 30 meters, or 1 meter in front of them, or a meter behind, over their head, behind them, or 5 meters behind them. And when we looked at when they pushed their buttons, then we found this inverted U-shaped relation between response times and, response times and passing distance. And when we tried to understand that, we looked at optical acceleration, and for these 4 different trajectories, optical acceleration at 4 different time series. So this would be the ball that would fly 5 meters over your head. This would be the ball that fly 5 meters in front of you, and these were the closer ones. And then if you looked at optical acceleration and just defined the threshold, then this would be the situation that people would know earliest, push their button, and that's why this would be the lowest point. And this inverted U is actually this inverted U. One thing to note is, just for kind of education, I use this figure more often, and then I typically ignore the fact that there are 3 points here. It's not in the legend anymore because I don't want to confuse other people, but actually it's pretty important. Here, the other thing that the solid squares are this velocity ratio thing, right? So that's another way of knowing that optical speed is not constant, and it's not exactly the same as you would do as if you would take acceleration, but it's doing this qualitatively the same thing. So that was good. So one of the things in this cave, of course, was that it was rather small. It's only 3 meters by 3 meters. So when I say we had these balls flying 5 meters in front of you and 5 meters behind you, that was outside of the cave. So we couldn't do much catching. It would ruin the cave. And although we're not using it anymore, at that time I didn't want to do that. But we did do some catching. But the thing is, in that cave, all the catching could be done by just moving your hand around, right? Because there's only a few meters, and that didn't work out very well. So we came up with a solution. We did some heading, because then you had to move your head, and that worked out kind of well. But still, that was kind of the last experiment in the cave. It's not only because we moved from Amsterdam to other places, but also because I thought we needed more space. And that's how we ended up doing the kind of experiments in the setting that Days has shown a second ago. So, patterns of judging passing sight are consistent with the use of optical acceleration. Now the question is, are patterns of running initiation times the same kind of logic also consistent with the use of optical acceleration? And when I say optical acceleration, I mean optical velocity not being constant. So these were this is the cave, and the idea was that we do real catching. And we went to this setting that we actually ran maybe 5 or 6 experiments in now, and those are pretty tedious experiments. The experiments not too bad, but really digitizing all the data, we had to use a lot of students for that, and didn't make a lot of friends. But there is lots of space here. So the task that I studied and that I'll be talking about is these people are catching fly balls, and we make sure that they will be able to reach those balls. The thing that Days did a second ago was also have fly balls that were out of reach. We projected these balls with a very cheap ball throwing machine. So the co-author, Harjo the Poel, I think he bought it for $200 on the internet, which was a good thing because for the funding situation. But this will become important in a second. And actually in one of the experiments we also put an eye tracker on our participants. So this is what the participants would be experiencing. This is the type of experiment that we're running, and when we had the experiment that Days was talking about, at some point they would yell no, right? And actually we used this eye tracker because initially we didn't know how to record audio, and we weren't sure that the video camera would pick up the audio, so we figured why not put on an eye tracker because it has audio, which was a silly idea, but in the end So this is the kind of type of patterns that we're looking for, and actually you can look at different other trajectory variables that should play a role. So over here we had passing distance, so the distance that you need to run to get at the interception location should have, if it's farther away, you should start running earlier. But you can also look at if balls fly higher trajectories, what would that do? And if balls fly higher trajectories, you would predict, just from doing the same type of analysis that that was over here, they should start running later. And if the most interesting thing actually I think is if balls would fly trajectories that would make that you had to cover the same distance in the same time, but this ball would come from a longer distance from where you would be standing, then you would also predict that from optical acceleration that people would start running earlier if this ball came from a longer distance. So we had a nice experiment with different heights of these balls, different passing distances, different distances from where they were launched, back and forth. And we were about to run our ANOVAs when we realized that this ball machine was not doing a very good job. Basically, our trajectories, our ball trajectories were very variable. So these balls, they didn't fly all over the place, but they were not very reproducible. So we couldn't, or it was difficult to kind of find our different cells of our ANOVAs from all these kind of balls all over the place, which was a pity. And I struggled a long time with that. Initially I was kind of disappointed, but later I figured this actually would be an advantage, because this is really more like real catching balls, right? They don't always end up at 2 meters or 4 meters and fly 6 meters or 8 meters. No, they fly all over the place. So from the idea of just trying to think about what I would like to understand, how people catch fly balls, this is nice. But from the perspective of and analyzing these things, it was a problem. So we'd like to do ANOVAs, repeated measures ANOVAs, because the power of that type of analysis, but basically what I have continuous variables. So I have passing distance, I have height, I have distance, and those are all continuous variables. So the alternative would be something like a multiple regression type thing, but then I would lose the repeated measures thing. That would be powerful. And then after a while I found a method on the internet that seemed to do a multiple regression and also do the repeated measures type of thing, which sounded like the way to go. And actually I think that's a very powerful method. It's called linear mixed effect regression. And I'm not going to explain to you all the details of that, but basically it's a multiple regression that we know. So here's the distance of the ball, here's the height that this ball flies, this is the absolute value of how far this ball will fly, will land away from you. Here's your running initiation time, and this log is only there because we wanted to be sure that we didn't our residuals needed to be close to normal, normally distributed, so that's what this log is for. This is the weird thing. This is called a random factor, a random effect, and this makes that this is the multiple regression model actually takes into account that the average running initiation time in this case is different for all participants. So you're doing a within participant kind of analysis, and you can do many more things, but this was the model that fit the data best at where we were. And this is our data, so this is all individual trials. So we don't do averages across many repetitions of a trial because they are all over the place. And these are the two factors that came out significantly from this model. So the height of the ball, let's see this over here. If a ball flies a higher path, then you start running later. Okay, so that's in line with our hypothesis. If it lands farther away from you, larger peak distances, passing distances, you will start running earlier. Yeah, okay, that's true too. The only thing that we didn't find, and I'm kind of disappointed about this because I think that's the most interesting thing, would be this one. So we're still running experiments. Yes. Sometimes I have to think about my. So R squared. You can compute R squared. It's about a third of the variance. So it's not bad if you consider that we'll look at every in each individual trial here and not do averages. So running initiation times are consistent with the use of optical acceleration, and when I'm saying optical acceleration, I really mean this qualitatively, right? The effects are in the right. I'm doing linear regressions, but really I think it's about the same shape that I'm looking for. So this could be the optical acceleration per se. It could be this velocity ratio, but even a fractional derivative of position of the order 1.8 would also give you the same predictions that I showed you. So I think it's in the right direction, and I still think that at some point we'll be able to kind of connect the stories that I'm telling here with the story that Dace just told you a second ago, 20 minutes ago. And we're working on that. So I think that's what I wanted to share with you today.